We're going to take a look at chapter 1, part 4, or measurements, okay, or section 4. So SI units. SI units are the standard units that are defined by the international system of units. So this organization defines what each of these units mean. They're in charge of making sure the entire system, the SI units, are have the same length of a kilogram, a meter, a second, a Kelvin, a mole, etc. All right, good. The SI part of it, by the way, it's weird that it's SI, not IS. SI, originally, this is a French organization or a French system. So it's La Système Internationale of units. So that's where it came from. So in the metric system or the SI units, we have a set of base units. All of these base units, and here are 5 of the 7, the 2 that we're missing. So mass, length, time, temperature, and amount of a substance are the 5 base units that we're going to use. The 2 missing are the candela, which is intensity of light, and amp, which is a measurement of electricity, current and electricity. So those 2 we're not going to use at all. So really at all. So we're going to focus on these 5: mass, length, time, temperature, and the amount of the substance. Each of these units has a base unit. So the base unit for mass is kilogram. That's the only one with the prefix kilo or any prefix. The rest are not. Meter is just the base unit. Second is just the base unit without a prefix, so on and so forth. So each of these units is what we call a base unit. If you think there's another thing called derived units. Derived units are the combination of these things mathematically. So all of the basic types of measurements you would make in a lab: measure something with length, or weigh something out, or time something. All of these are the base units, and then they get more complex and they get turned into derived units, which we're going to cover in a little bit. In fact, we're probably going to go over those together. Length. Okay, so I'm going to show you this first one, and then I'll just kind of walk through the rest. So originally, the length of 1 meter was measured as 1 1/10,000,000th of the distance from the North Pole to the equator. That's great. That's something that is not going to really change, the distance of the North Pole to the equator, minus the fact that magnetic north versus true north are different, but the distance between the North Pole and the equator is always going to remain the same. But it seems a little bit weird to have to know that distance in order to measure the original length of 1 meter. And not to mention, if we do make it into the cosmos or something, if you end up on Mars, we're not going to have that base unit of measure for 1 meter, because we don't necessarily know the North Pole to the equator, because we don't have that on some other planet. So at this point, the SI units basically said, all right, we need something that is related to the physical world that will not change no matter where we are. You can measure this in New York City. You could measure this in China. You can measure this anywhere in the universe, and you should get the same exact value. And so they came up with a new definition of a length of 1 meter. And that definition is the distance that light travels in, well, first of all, in vacuum, I should say, in 1 in 299,792,458 of a second. Okay, so that is the length of 1 meter, the distance light travels in that very, very short amount of time. But that's good. So now we can actually, well, we know how far light travels in that time. We can figure out exactly what a meter is. We would never do this day-to-day life, but it's important to know that it's no longer pegged to a distance on Earth. It is now pegged to this concept of the distance light can actually travel. Mass, on the other hand, is very different. Mass was originally, well, until 2019, mass was measured by this platinum iridium alloy cylinder that was isolated in France. And then they made 40 extra ones and they send them around the world to say, okay, this is exactly a kilogram. So watch those 2 videos. It's really interesting, especially the first one. It's really interesting. You can see that they now measure it based on something slightly different. It's a cylinder of silicon is the new measurement for the mass of 1 kilogram. Time is based on vibrations of a cesium atom. But again, I could measure the vibrations of cesium atom here, or I could measure them on Mars. They should be the exact same thing. They will be the exact same thing, I should say. Temperature. So temperature is based on 2 different things. The one that we're going to focus on the most is this unit, or this conversion. So you do need to know this conversion. Please know this conversion. Okay. Celsius 0 degrees is based on the freezing point of water at, and 100 is the boiling point of water at sea level. Okay. But that's not what we use as the base SI unit. Although 1 degree Celsius is equal to 1 degree, 1 degree Celsius is equal to 1 degree Kelvin. So they're on the scale, they're just shifted. 0 degrees Kelvin is equivalent to the absolute 0 when there is no molecular motion whatsoever. So that's the original, that's how we base 0 degrees Kelvin, and we can just go up from there. A couple of things. Kelvin is always going to be higher than Celsius, and it will always be positive. Okay, so if you ever have a negative number for Kelvin, you're doing it wrong. Kelvin's always higher than Celsius. So if you do a conversion and your Kelvin is lower than Celsius, you've flipped it, you've done it wrong. Okay. I've not talked about Fahrenheit at all, and that's okay. I don't need to talk about Fahrenheit because we're never going to use it in class. All right, but the just for completeness, the conversion is right there. All right. By the way, if you ever quickly want to convert Celsius into Fahrenheit, usually just double it and add 30, and that's about the right temperature. All right, let's take a look at prefixes. So each of these base units can also get a prefix, and it's going to multiply it. So 1 meter is equivalent to 1 meter. But if I say, all right, 1 kilometer, it's basically saying equivalent to 1,000 times that, or 10 to the 3 times that. Okay, 1 gigameter is 10 to the 9th times that value. So we use prefixes to increase or decrease the number just to make sense of it all, right? I'm not going to say, oh, I've got to travel, 10,423 millimeters in order to get to the store, right? That doesn't make any sense. What you're going to do is you're going to use a kilometer because that makes much more sense in terms of distances you would actually travel. So these prefixes are often used, and we're going to go over unit conversions and all that stuff to make the numbers make more sense. So be reasonable when we're writing out scientific papers, or we're just talking in general, and we're not going to use really giant numbers to do that. So here are all the prefixes. The ones on top are the ones that are going to increase the size of the number. So tera, giga, mega, kilo. And then the ones on the bottom are ones that are going to decrease the size of the base unit. So deci is 1/10 of a base unit. Centi is 1/100th of a base unit. By the way, those are a little bit easier to memorize too. How many years in a century? 100 centi is 1/100th. How many years in a millennium? 1,000. Milli is 1/1000th, right? The ones that we're going to use the most: kilo, centi, milli, micro, and a little bit less so, but you do use nano. Micro and nano, you're going to see a lot more in physics and in drug delivery and those types of things. So you should know those above all else. And then pico and femto, those are much more physics terms because you're talking about really, really tiny amounts. But know these. Yeah, these are important conversions to know. By the way, the last thing that I do want to point out is the fact that these jump by 3. Okay, so each of these, it's 3 more orders of magnitude, 3 more orders of magnitude, 3 more orders of magnitude, 3 more. So if you know milli and you know the order, micro +3, nano +3, pico +3, femto +3. So if you know the order, you just multiply it out, or just add 3 each time you make that jump. Okay, good. So next up, derived units. So derived units are based on the idea of these base units. So essentially when you perform math on these things, you're going to combine them. So when we mathematically combine base units, we get a derived unit. We're going to do these determining the SI derived units in class together, but the ones that I want to ask you are, okay, let's do these first two. So again, there's our base units. How do you find the area of something? Well, if I want to find the area of a field, for example, I'm going to take the length times the width of that space. Okay, if you want to find the area of a room, which you typically do when you're like buying a house or something, well, a length is measured in length in meters. Width is also a length measured in meters, so you end up with meters squared. Okay, so again, we have the base unit. We have another base unit. And that right there is our derived unit. So length times the length gives me area. What is the derived unit for area? It is meters squared. Same question for the next one. Volume is generally length times width times height. So length times a distance is going to give me meters cubed. Meters cubed is going to be my derived unit for a volume. How about the rest of these? When you think about a velocity, what are the derived units you would use for the metric system for that? Acceleration, force, work, pressure, all of those, energy. So we're going to go through these, so make sure this is part of the homework, essentially. I'll put this in homework form, but you should do this, and you should do this before we get to class. Okay, with that said, let's take a look at two derived units that are really important. Volume. Volume is one that we're going to use all the time in chemistry. The way that we typically look at it, so 1 meter cubed is a pretty giant space, actually, because the two values that I want you to know are 1 decimeter cubed is 1 liter, and that other one's most important. 1 centimeter cubed is 1 milliliter, and it kind of gives you length times width times height. So the ones that are important, 1 decimeter cubed is equal to 1 liter, and this is the more important one, centimeter cubed is equal to 1 milliliter. You see that a ton in chemistry whenever we're doing conversions within volumes. But anyway, volume is the amount of space occupied by an object, how much space it takes up. Density is based on the mass and volume combined. So the density is, we know that D is equal to M over V. And again, this is going to come down to a derived unit as well. So on top we have grams, and we determined this earlier that this is meters cubed, grams over meters cubed, and volume. So grams over meters cubed, we have the amount of stuff within a given space. But again, we have mass. That is a base unit divided by the volume, which was our derived unit. And we have now a new derived unit, which is density. Okay, mass over volume. So again, these derived units are essentially everywhere, but you'll notice that they're always coming from those base units. Talking about a volume in meters cubed is a little bit strange because typically we talk about liquids and we talk about liters. So let's finish the talk about those by saying the following. Solids, liquids, and gases. Whenever you're talking about a solid, the density is generally reported in. And this is a little bit important just because you're always going to see these values attached to solids, liquids, and gases. A solid density is going to be measured in grams per centimeters cubed. A liquid is generally reported in grams per milliliter, and gases are typically reported in grams per liter. Okay, so each of them has their own unit, but again, they're all the same thing, mass over volume, giving us the density. But solid, liquid, and gas are generally reported differently in each. So when we're looking at density as the last little bit here, let's take a look at these 4 boxes that we have. We're all going to kind of compare them to A, okay? So if I add more mass, okay, so if I take box A and I add more objects, or I add more of the mass, we now have a situation where the density of A is actually less than the density of B because B has more mass. We'll notice that C has more volume. Maybe I'll put this down here. That makes more sense. C has more volume. By increasing the volume, we've actually made it less dense because we have less mass per unit area. So there's less mass per unit area. So the density, in this case, density of A is actually greater than the density of C. How about the density of D? Well, the other way we could look at it is, although they're not the same objects, it is still more mass. Doesn't really matter what I have in there as long as I have more stuff, right? It's not empty space. I've added these red little things along with these cubes. Ultimately, more mass in that same unit volume means that the density of A is actually less than the density of D. Okay, so again, that's how density works. And I will leave you guys with this. You're sitting in a rowboat on a small lake. You have a brick in your boat, and you toss the brick out of your boat into the lake, where it quickly sinks to the bottom. Does the level rise? Does the water level rise slightly, drop slightly, or stay the same? Water level in the actual lake. It's going to be minuscule, but it will make a difference. So does the water level rise, drop, or remain the same? All right.